How AI actually learns. Explained simply, no jargon. Every day, millions of people talk to AI models like they're talking to something that understands them. But what's actually happening inside these systems has almost nothing to do with understanding in the way you'd assume. In this video, we're going to break down, in plain language, how AI actually learns, why it gets things wrong in very specific and predictable ways, and why the world is currently spending over $2.5 trillion trying to build more of it. Let's start at the very beginning. What is a neural network, really? Strip away the buzzwords, and a neural network is just a very large mathematical function. It takes an input, like a sentence, and produces an output, like the next word in that sentence. Inside that function are billions of adjustable numbers called parameters. Think of each parameter as a tiny dial. When you turn all the dials to just the right positions, the function gets very good at predicting what word should come next, given everything that came before it. The largest AI language models today have hundreds of billions of these dials. Training a model means finding the right position for every single one of them. That's the entire task. Nothing more mysterious than that. So how do you find the right position for billions of dials? This is where training comes in. The process starts with data, an enormous amount of text pulled from books, websites, articles, and countless other sources. The model is shown a piece of this text with the last word hidden, and it has to guess what that word is. At the start, with all its dials in random positions, its guesses are essentially garbage. But here's the key mechanism. After each guess, the model is told the correct answer, and a process called backpropagation nudges every single dial a tiny amount in the direction that would have made the correct answer more likely. Do this once, and almost nothing changes. Do it billions of times across trillions of words of text, and something remarkable happens. The dials settle into positions that capture genuine patterns in language, grammar, facts, reasoning styles, even coding syntax. Not because the model understands any of it the way a person does, but because those patterns are, mathematically, the best explanation for the data it was shown. This is why scale matters so much in AI right now. More data means more patterns to learn from. More parameters mean more capacity to store those patterns. And more computing power means you can actually run the training process on that much data in a reasonable amount of time. This is exactly why the biggest tech companies in the world are collectively spending several $100 billion a year on chips and data centers. They're not buying intelligence directly. They're buying the raw capacity to run this pattern-finding process at a scale no one has ever attempted before. Now here's where it gets interesting, because this training process, powerful as it is, also explains almost every strange limitation people run into with AI.
Take the famous example of AI models struggling to count letters in a word like strawberry. This seems like it should be trivially easy for a machine. But models don't actually process text one letter at a time. They break text into chunks called tokens. So strawberry might become 3 pieces: ST, raw, and berry. The model never sees the individual letters inside those chunks. It's reasoning over bundles, not characters. So when you ask it to count how many times a specific letter appears, it's doing something closer to guessing than counting, because the information it would need is partially hidden inside those token bundles. Then there's the hallucination problem, when an AI states something confidently wrong. Remember, the model isn't retrieving stored facts from a database. It's predicting the statistically most likely next words based on patterns in its training data. If the training data contained a mix of correct and incorrect information on a topic, contradictions on the internet, outdated facts, or simply very little coverage of a rare subject, the model's predictions in that area will be shakier. And because its knowledge has a fixed cutoff date, anything that happened afterward is invisible to it. It will still generate a plausible sounding answer, because generating plausible answers is literally what it was trained to do. Plausible and accurate are not the same thing, and the gap between them is exactly where hallucination lives. There's also a subtler issue researchers now call sycophancy. Because these models are fine-tuned to be helpful, and human evaluators tend to rate agreement as more helpful than disagreement, models can drift toward telling you what you want to hear rather than what's actually true. Studies on this effect found that sycophantic responses increase a person's confidence in their own ideas without making them any more likely to be correct. You feel more certain, but you haven't gotten any closer to the truth. It's a quiet, easy-to-miss side effect of training a system to optimize for how helpful its answers feel, rather than purely for accuracy. So why does any of this matter to you as someone just trying to use these tools day to day? Because understanding the mechanism changes how you should use it. If you know a model can't literally see individual letters, you stop being surprised when it miscounts them, and you double-check anything that requires exact character-level precision. If you know hallucination comes from predicting plausible text rather than retrieving verified facts, you learn to verify anything important, especially about recent events or niche topics. And if you know models can lean toward agreeing with you, you get in the habit of occasionally asking one to argue the opposite side of whatever you just discussed, just to stress test your own thinking. None of this makes AI useless. If anything, understanding exactly how the system works makes it far more useful because you know precisely where to trust it and where to double-check it. A tool that can write, summarize, translate, and code at a genuinely impressive level is still a tool built on pattern prediction, not human-style understanding. Both of those things can be true at once.
And that brings us back to the trillions of dollars being poured into this technology right now. Companies aren't betting on AI becoming magically all-knowing. They're betting that scaling up this same pattern learning process, more data, more parameters, more compute, will keep producing systems that are increasingly useful for an increasingly wide range of tasks, even while carrying the same fundamental quirks we just walked through. Whether that bet pays off at the scale being promised is genuinely an open question, and one worth watching closely over the next few years. But the mechanism underneath it is not a mystery anymore. It's billions of adjustable dials, tuned by an enormous amount of trial and error, producing something that behaves remarkably like understanding without actually being understanding at all. If this helped the way AI actually clicked for you, follow AI Signals. New videos breaking down exactly how this technology works in plain language every single day.